To explain the seeming contradictions between particle and wave behavior and the impossibility of measuring certain quantities simultaneously with perfect accuracy, the Heisenberg uncertainty principle, Erwin Schrodinger developed the wave function called psi in 1926. Significant work done at the same time was done by Paul Dirac, and the two gentlemen shared the Nobel Prize for Physics in 1933 for their work on quantum mechanics. In classical physics, which again is stuff you and I can see with our eyes, if all the forces on an object are known, we can use Newton's laws and we can find everything else. Position, momentum, acceleration, whatever we want to find. If we know the forces, we know what's going on with the object. Psi performs a similar function in quantum physics, with the major difference that you only find the probability of a particle's position, energy, or momentum. The key word is probability, not exactly. You cannot find out exact things anymore at the quantum level because of the uncertainty principle. Well, that explains it. The reason you can't is you can't. That's how nature's working. So psi for quantum mechanics is equivalent for knowing the forces in classical mechanics. An example of the use of psi is in the double slit experiment for electrons. Young did the experiment with photons with light, and he showed that there was a unique interference pattern. So remember, we had the two slits here. There's one slit and there's another slit. When light came through, you would have expected that you'd have a bright patch of light here and a bright patch of light here, and you didn't have that at all. You actually had a bright patch here and then bright patches all the way off to the either side here, okay? Indicating that the light was acting like a wave and interfering with itself and creating these different maxima, just like water waves do. Now electrons showed the same pattern. So what was happening, if the electrons are just considered as particles and you know exactly where they are, an electron can't split in half. It can't go here and then come over here. It has to go straight. However, and in that case you would have no interference. You'd have a whole clump of electrons here and a whole clump here. But what happens is electrons are represented by the wave function psi, and this wave function represents all the knowledge we have about the electrons. And if we have a stream of electrons hitting these two slits, their wave functions will interfere, and we will get an interference pattern here just like we did with light. Thus, the interference patterns that we see are explained by analyzing the wave functions and their interactions. Once you have the wave function, if you square the wave function, psi squared, that gives you the probability of where a particle is. Again, it doesn't tell you exactly where it is, it just gives you the probability. This was first suggested by Max Born. And again, just to show the absolute beauty of the wave equation, here it is for one specific problem. Okay, this is, let's see, a second order differential equation. This is a partial derivative. This is the del operator. You won't have to know any of this stuff, well, frankly, till you get to college. But the nice part about this is very elegant, very beautiful, and there's a number of things you can get from it. You can solve for psi by solving this equation, and that'll tell you everything you need to know about the particle. And we'll just take one more step. This little guy over here, I h bar is just h divided by 2 pi, Planck's constant divided by 2 pi, partial derivative with respect to time. Not important right now, but if you take this and act on the wave function, it will give you the total energy of the system. So that's what was meant earlier by saying if you know psi, you know everything you need to know about the particle. But again, this is college level physics, even beyond AP. The solutions to the wave equation, Schrodinger's wave equation, show how the periodic table, electron orbitals, atoms, molecules, chemical bonds, etc., how they work. It describes the microscopic world. And again, microscopic, it really should be submicroscopic, which is so different and counterintuitive to what we see at our level. The uncertainty and probability concepts contradict what can be seen at the macroscopic level, where we know pretty exactly where things are and how they're moving. But that's not how nature works, and that's why the Schrodinger wave equation is so very helpful in understanding how it works. And the fact that all the solutions of it and the predictions actually show how objects work on the macro level, how chemistry works, how biology works, makes it an incredibly powerful tool.